Hello everyone. We move into a new section called Taylor, or its special case Macquarian series, Taylor series and Macquarian series, which follows from the last discussion of power series. And the main result that we have is the following statement. That is, if we assume that f prime, f double prime, up to the nth derivative, and also the n plus 1th derivative, all exists over the interval, let's say from a to x, then you can write f of x into the form of f of a plus f prime of a, x minus a, plus f double prime of a divided by 2 factorial x minus a square, and this pattern continue up to the nth derivative divided by the n factorial x minus a to the power n, and then plus a remainder depending on n and also the point a and x. Here the remainder, our n ax, has several forms. One possibility is that you can write it as f of n plus 1 derivative divided by n factorial evaluated at t, x minus t to the power n, x minus a. And then the second one is also the n plus 1 derivative divided by n plus 1 factorial this time, and x minus a all the way to the power n minus 1. Indeed, there is a third form which is written in the integral form. So you're integrating the n plus 1 derivative divided by n factorial and x minus t to the power n with respect to dt. And the first form is called the Cauchy form of remainder. The second form is called the Lagrange. And the third one is called the integral form. Here, the t is a certain point, so is some point lying in a to x, not including the boundary. So t is actually appear in various places. So this t is actually some point which is not known, but somewhere between a and x. It doesn't have this problem with the integral form because you are integrate over the t. So t is a dummy variable that varies between a and x. Okay, so in most cases that we are interested in is that when n goes to infinity, let me write here, when n goes to infinity, the remainder actually goes to 0. So in other words, in most cases that we're interested in, you can write f of x to be equals to the sum of the nth derivative evaluated at a and then divided by n factorial and x minus a to the power n, where n goes from 0 to infinity. So we will have this kind of expansion. This is called a Taylor expansion of the function f about the point a. So in the case when a equals to 0, that is f of x is a Taylor expansion about the point at the origin, a equal to 0. So you would have this simplified form. And this simplified form is called the Macquarian expansion. Which is essentially a special case of Taylor expansion. So we would discuss as one more remark, that is, if we assume all the derivatives exist from the first, second, up to the nth derivative, and n plus 1th derivative exists, actually what it means is that all these first, second, up to the nth derivative, they're all continuous. Whereas no guarantee the n plus 1 derivative is continuous. But because the derivative, the n plus 1 derivative exists, so this implies the earlier function before differentiation must be continuous. And since the nth derivative is continuous, not only exists, it will also imply the previous the function before the nth derivative must also be continuous, etc. So you can then push back all the way to the first one. So it turns out that if we assume the n plus 1th derivative exists, all the previous one not only exists, would actually be continuous. So, and we will talk about the remainder more later. So let's look at some important example, namely that we look at exponential function. Okay. So example. So let's look at example f of x to be exponential. Now for this function, any derivative exists and equals to itself for all n bigger than or equal to 0. So that's no problem concerning the derivative itself. And so according to the Taylor expansion, I will be able to write the expansion into the form of the sum of f nth derivative about 0 divided by n factorial and raised to power n. N goes from 0 to infinity. So this is a Macquarian expansion. All right, so to get this expansion, we need to compute all the derivative evaluate at the point 0. As you can see here, I'm writing out in full these first few terms. All right, but then the nth derivative of the function, because it's equal to exponential, so if you evaluate at 0, so you would put 0 into exponential, which is equal to 1. And because of that, the Macquarian expansion of this would simply be, if you look at the first term, then this would be just 1 plus, and you look at the second term, which is still 1, so you would have 1 over 1 factorial times x, and then you look at the second derivative, and that is of course just still 1, but this time is divided by 2 factorial, and then you have x squared, and then you have the third derivative at 0, which is still 1, and divided by 3 factorial this time, and this pattern just continue up to the nth derivative, which is still 1. So I have 1 over the nth derivative x to the power n plus etc. And this turned out to be the Macquarian series for the exponential function. And we can do now a Taylor expansion, not necessarily about the point, in this case, a equal to 0, so that's why you get a Macquarian. So if we do a general expansion, which is this would become a new example. So we get we still have f of x e to the x. So we want to find the Taylor expansion of the exponential, let's say about x equal to 1. So in that case, let's start with f of x to be e of x. So according to the Taylor expansion formula, you would get the nth derivative evaluated at 1 divided by k factorial, n factorial. In fact, it doesn't matter whether you use k or n, but you just need to be consistent. But this time, you get x minus a, where a equals to 1 to the power n. So n goes from 0 to infinity. So you would have this expansion instead. And so since the nth derivative of the exponential function equals to the exponential itself, so when you plug in x equals to 1, this will simply be 1, or just e. In other words, the Taylor expansion would be given by, you're going to replace this nth derivative evaluated at 1 by e, because they are the same for every derivative. And so that becomes a common factor where you can factor outside, and you would get x minus 1 to the power n factorial, and n goes from 0 to infinity. So this would be the Taylor expansion for the same function, but this time about the point x equals to 1. But those with a sharp eye might have already noticed that you can actually try to look at this expansion in a slightly different fashion, that you replace little x minus 1 by capital X. And so if that's the case, this infinite sum, as we saw now, represented by just e to the capital X, because it's a Taylor, it's a Maclaurin expansion for the exponential with respect to capital X. And now if we substitute back for little x, so capital X becomes x minus 1. So we would get this relationship. So that's interesting, because the left-hand side is exponential, the right-hand side is e times exponential of x minus 1. But of course, we know that we can multiply the two. So this would becomes 1 plus x minus 1. So that is back to e to the x. And there's, of course, no contradiction whatsoever. All right, so that's a Taylor expansion of the exponential function about the point 1. So let's do at least one more example, which is different one, an important one. So this time we're going to look at if f of x is equal to sine of x. Let's do it a Maclaurin expansion, so it's a Taylor expansion about x equal to 0. So they're the same thing. All right, so we need to compute for the derivative, and this is a little bit more complicated than the exponential. So if we look at this, we differentiate the sine, we get cosine. But if we differentiate cosine, that means the second derivative, we get minus sine of x. So if we differentiate once more, the third derivative, you would get minus cosine x, and the fourth derivative, you would get back to sine x, because you differentiate cosine once more, so you get 2 negative sine this time, so you're back to sine. And then the pattern just repeats itself. And I will not repeat it. So essentially, you can summarize this by saying that the odd derivative, you would have minus 1 factor to the k minus 1. So the odd is 2k plus 1 derivative. Let me write this a little clear. And you get cosine x. And the even one, you get sine x. You also have minus 1 to the power k. Okay, so in particular, if you plug in 0 into the even one, you get 0. But if you plug in the odd one, because it's a cosine, you would get minus 1 to the power k plus 1. All right, having done that, so the formula, the Maclaurin expansion tells us we would have computed all the derivative raised evaluated at power 0 and 0, and you will get this. But you now divide this into two. One is even, one is odd, and you will see that when it is even, you would actually get 0 contribution. It's only when it's just the odd power you will get a plus minus 1 depending on what k is. So if we be careful enough, you will actually see that you can actually rewrite this into the form of minus 1 to the power k. This time is now k. So k goes from 0 to infinity, and this would becomes sine x of 2k plus 1 divided by 2k plus 1 factorial. So the n will only exist when you consider those in the form of 2k plus 1. Next time.